All right. Good morning. Let's get going. So in today's lecture, we continue with the operational amplifier, op-amp for short. And what we're going to do is just build up a bunch of fun building blocks using the op-amp. Okay. As a quick review. To quickly review what we've seen about the op-amp, so we represented the op-amp as a device that looked like this, where the amplifier had an incredibly high gain. So if I had a small voltage difference here, so I call this V plus and this V minus with respect to ground. And if I had a small voltage difference, then this gain here would multiply the difference by a large number, and thereby giving me an output that was on the order of 1,000,000 times greater than this difference. And because of that, when I use the op-amp in a mode like this, without any negative feedback, the output would usually thunk up to the positive rail or the negative rail. So we also saw that it had infinite input resistance, so that the current flowing in here or here was 0, and also had 0 output resistance. Now this is my ideal op-amp, where irrespective of what load I connect here, the op-amp could supply pretty much any current. Now in practical op-amps that's not the case, but suffice it to say that when used as an ideal op-amp, the output impedance, the output resistance is going to be 0. So the op-amp is a huge workhorse of the analog industry. You will see, based both on what you've done on Tuesday and Wednesday, but also today, that it's very, very simple to build circuits using the op-amp. Okay, you don't have to, when you use the amplifier, you don't have to worry about things like nonlinear analysis. You don't have to worry about, am I really meeting the criteria for saturation limits and so on. To some extent, you have to think about that with the op-amp too, because if the output hits the positive rail or negative rail, it isn't going to behave like you expect it to. But fundamentally, with this primitive model, with this ideal model, it becomes really simple to build circuits with the op-amp. So therefore, it's become a key building block for circuits. So when circuit designers build analog circuits, very often their primitive building blocks are really an amplifier of this sort, an op-amp, resistors, capacitors, and some of our other primitive building elements. If you look at the course notes, the readings are there are a bunch of examples solved in the chapter 16, and you will see that using the op-amp, it is indeed possible to build current sources that look like, more or less ideal current sources. It's also possible to build voltage sources and so on. So it's an incredibly neat building block using which you can do all kinds of cool stuff. So in this course, you will see a whole bunch of example circuits using the op-amp. In today's lecture, you will see things like a subtractor. We'll also see integrators and a differentiator. And then in your lab 4, you will build a really fun mixed signal circuit involving both digital and analog components. And you will build what is called a digital to analog converter using the op-amp. Okay? And of course, I can build all our good old amplifiers, and circuits of that sort. In a later lecture, we will also see how we can build filters using an op-amp. This is going to be using the knowledge you've learned in terms of connecting resistors, capacitors, and inductors together and doing a frequency domain analysis. Well, we can throw in the op-amp in there and build filters too. Okay, this is just to give you a preview of upcoming attractions. And for today, I'm going to focus on these circuits. Okay, so I won't be covering any new theory or any new set of foundations, but pretty much take the simple properties that I've explained to you about the op-amp, and using those simple properties, very quickly build up a bunch of circuits that you can use to analyze signals in a variety of ways. So let's start with the following circuit. So with op-amps, I start with this little guy. And what I'm going to do is use two voltage sources, V1, and this is a resistor, not an inductor, and value R1, value R2. So I have a voltage connected by a divider, voltage divider to the plus input, and I'm going to provide some negative feedback in the following way. This is going to be R2, the same as this one here. A resistor R1, and then a voltage source V2 that I connect out here. So notice that, and I take the output V out out here. And that V out, of course, is with respect to ground, and R2, V1, and V2 are also connected to ground. So what I'm going to do is analyze the circuit in two different ways, and as I analyze it, describe some other interesting properties to you. In the last lecture, the technique I used to analyze op-amps was one in which I replaced the op-amp with its ideal model involving a dependent source and so on with a large gain, A, and showed that I wrote the expression, and then I let A increase to infinity and took the limits and got an expression that was independent of A. And then in recitation yesterday, you would have covered another technique, which makes it much simpler to analyze op-amps. Okay, let me very quickly review that method. We fondly call that technique, there's no formal name for it, but we fondly call that V plus more or less equal to V minus method. Okay? But this is also variously called the virtual ground method and so on. But we shall call it the V plus more or less equal to V minus method. So the insight here is that whenever I use the op-amp, okay, in a way in which I'm giving it negative feedback. Okay, so I'm feeding some portion of the output to its negative input. Okay, I'm giving it negative feedback. That's one property. Second property is that my inputs, V1 and V2, and my resistance values are chosen such that the output is not in saturation. Okay, so the op-amp is not at the plus rail, plus Vs rail, or minus Vs rail. Rather, it's somewhere in the middle in its active region. When that happens, we claim that the V minus and V plus for the op-amp are more or less equal. Okay? And to give you some intuition as to why that is so, notice that, let's say the output is 6 volts. Okay? And my supply is plus minus 12. If this is 6 volts, and the amplifier is a gain of 1,000,000, okay, 10 to the 6. Okay, to sustain a 6 volts at the output, all I need is a difference of 6 microvolts here. Okay, 6 divided by 10 to the 6 is the difference between V plus and V minus. Okay, it's very, very, very small. It's so small as to make V plus more or less equal to V minus. Okay, all it takes is a very small differential voltage here to give you a 6 volts at the output. So the key thing to observe is under negative feedback, when the op-amp is not in saturation, the property that V plus equals V minus holds. Okay, and the way it works is that it's not that it's a magical property, it's simply that when I apply negative feedback, the negative feedback is such that it will force this V minus node here to be at more or less the same voltage as V plus. Okay, remember when in doubt, simply go back and remember and think about your anti-lock brakes example we did last time. So if, for example, V plus increases, the output will increase, and so will the voltage here, and tend to make these two equal. So what we can do is, being rather tricky here, what we'll do is say, look, if we know for a fact that under negative feedback, the op amp is going to engineer these two node voltages to be more or less equal, then why don't I just use that fact to begin with and analyze my circuit assuming that is true? Okay? So this is just a bit of inverted logic here that says, look, the circuit is going to make that happen. So the circuit is going to make that happen. To analyze the circuit in its steady state, why don't I just go ahead and assume that to begin with? Okay, this again goes back to us wanting to be engineers here and do whatever's simple. Okay, and find the simplest possible way of getting someplace. So I'm going to use that method, the V plus equals V minus method. So let me just first write down some values that I know about. So I know that V plus is simply a voltage divider relation here. So that's V1 times R2 divided by R1 plus R2. Okay, and by the V plus equals V minus method, I know that this is going to be equal to V minus. And this is going to be true because, look, I am giving you negative feedback here. Okay, and we are going to engineer the values of R1, R2, V1, and V2 such that the op amp is not in saturation. Okay, so that's so we know that. The next thing that we know, let's say this is the current I. So if this current I flows here, know that there is no current going in here. Okay, op amp has an infinite input resistance, so there's nothing going in there. There's no current going in there. So if there's no current going in here, what must happen to I? Okay, remember, from the foundations of the universe, okay, the Maxwell's equations, and therefore KVL and KCL hold. Okay, KVL and KCL simply come straight from nature. Okay, you and I can't mess with that. Okay, bad things happen to you if you do. Okay, so nature, Maxwell's equations, KVL, KCL. So it's simply nature. So KCL applies here. Okay, so current comes in here, nothing goes there. Okay, so don't argue. The current has to go here, period. Okay, no ifs, whens, or buts. There's I coming in here, nothing goes there, so that current must flow here. There's no choice. Okay, it's from basic nature. So, so I can write down what my current I is going to look like. What's I going to look like? Well, I know V2, I know V minus. Okay, V minus is the same as V plus, and V plus is the expression given here. So I can write I as V2 minus V minus divided by R1. Okay, so let me keep track of those two, and then go ahead and compute V out. So my goal in life is to compute V out as a function of the two input voltages, V1 and V2. Okay? And just for kicks, I've gone ahead and computed some of the intermediate node voltages and currents. So how do I write V out? What is V out? V out is simply V minus, okay, from KVL. V out is simply V minus minus the drop across this resistor. Okay, so the drop across that resistor is simply IR2. Okay, so it's from good old KVL from the first lecture, a voltage minus the drop across the resistor is equal to V out. So therefore, it's simply V minus minus IR2. So one thing to be very cautious about, I'll tell you right now, is that the output here relates to the inversion of the voltage across this resistor R2. Okay, be very, very careful in that if I have a voltage across this resistor here, that impacts V out with a minus sign attached to it. Okay, so notice that IR2 is the voltage across R2, and V out relates to the negative of that. Okay, be very cautious That's one of the commonest mistakes, the commonest silly mistakes I've seen people make in solving problems like this. Okay. So let's go ahead and I know V minus, and I don't know I. Let me substitute for I for now. And that is V2 minus V minus divided by R1 times R2. Let me go ahead and collect all the V minuses. So V minus, I get a 1 here. Minus minus becomes a plus, and so I get a R2 divided by R1 out there. And then I minus V2 R2 divided by R1. Okay, that's V out. So now let me go ahead and substitute for V minus, and that is simply V1 R2 divided by R1 plus R2. That's V minus. And this character here is simplified to be R1 plus R2. Okay? Minus V2 R2 divided by R1. So what do we get? So I cancel these two suckers out, and what I end up with is V1 R2 divided by R1 minus V2 R2 divided by R1, which is simply R2 divided by R1, V1 minus V2. Okay, so what's interesting here is that what I've ended up building is a very primitive subtractor. Okay, so my output relates to V1 minus V2 multiplied by the constant factor given by R2 divided by R1. Again, as I pointed out to you at the beginning of this lecture, no new foundations today, no new theories, no new disciplines, no new laws. We're just going to take what we've learned. 3 simple things: infinite gain, infinite input resistance, 0 output resistance, plus this new thing, V plus equals V minus. Okay? And just armed with those 4 principles, we're just going to charge ahead and analyze a bunch of circuits. Okay, it's a lecture on pure applications today. Okay, so this is one way of doing it. There's another way of solving it. We can solve the circuit. Remember, whenever you see a linear circuit and you see 2 sources or 3 sources, okay, just think superposition, right? You see a linear circuit and 2 or 3 sources, think superposition. Okay, so we should be able to apply superposition to this. Okay, the op-amp is simply another building block. It's a linear circuit. So let's use and let's see if we get the same answer. Okay, let's try to solve the circuit using superposition and see if we get the same answer. So to do superposition, what I'm going to do is build 2 subcircuits. One subcircuit in which V1 is 0, and that subcircuit looks like this. So if I set V1 to be 0, then I get R1 parallel R2 going to ground. So if V1 is set to 0, then R1 goes to ground, and I get R1 parallel R2 here. And of course, I have a V2 as before. And this was R1, this was R2, and let me call that V out 1. I'm sorry, let me call it V out 2. V out 2 corresponding to that component of the output that relates to V2 acting alone. Okay, remember superposition? Okay, build 2 subcircuits, one that depends on V2, and another one that depends on V1. So let's do the second one too. Second one is V2 going to 0. So here's my little op-amp. And what I'll do is simply flip the op-amp just to see if we can identify some interesting patterns. Just flip the op-amp around. And this is V1 as before. And recall that V1 was going to the plus node through a resistor R1, and then I had a R2 to ground. Okay, and then let me short V2 to ground, and when I short V2 to ground, what happens? When I short V2 to ground, what happens is that the tail of R1 here goes to ground, and so it's as if the output is connected to the node V minus through a resistor. So it's as if the output V out 2 is connected to the minus input through a resistor. We'll draw it like this. And the minus input goes through a resistor R1 to ground. Okay, if you thought that patterns were important in the earlier part of the course, doing voltage divider patterns and current divider patterns, the amplifier pattern, the source follower pattern, op amps is all about patterns. Okay, you should remember 2 or 3 simple patterns and be able to write down the expression for those just by observation. Okay, so this is one common pattern that you've seen before in the very first lecture, and I just wrote it down in that manner. Okay, so let me go ahead and solve this circuit. So it turns out that this is also a pattern. I'll analyze it today, but in the future, V2 going to this node through R1 and then R2 to the output. You've probably also seen this in your recitation. This one is called a inverting connection. And this one here is called a non-inverting connection. Okay, so let's go ahead and do V out 2. So V out 2 is simply given by, notice that since this is ground, no current flowing here, this voltage is 0. If this voltage is 0, this voltage is 0 by the V plus equals V minus method. If this is 0, the current that goes through here is V2 divided by R1. Okay? And that same current must flow through the resistance R2 as well. Okay? If the current V2 divided by R1 flows through this resistor, the drop across this resistor is simply given by, let me hide this for a second, simply given by V2. So V2 divided by R1 is the current here. This is 0. So the drop across this resistor is V2 R1 multiplied by R2. That's the drop across this resistor. This voltage is simply 0 minus the drop across the resistor. Okay, so it's 0 minus the drop across the resistor, and that gives me V2. Again, remember, this minus sign comes in when I want to convert this to get the output voltage from that. So this is a very common pattern. It's called an inverting connection, where the output is some factor of the input voltage, and the factor is given by R2 divided by R1. Let's go ahead and analyze this guy now. So what is V out 1 equal to? So should I call this V out 1 because it relates to V1. So V out 1, so there's a V plus here. From our first lecture, okay, I know that V out 1 relates to V plus in the following way. I know that it is V plus times the sum of the resistances divided by R1. Okay? Based on the first lecture, this is true. V out 1 is simply an amplified version of V plus, but the amplification factor is given by R1 plus R2 divided by R1. And I know V plus too. V plus is simply a voltage divider action here. And I can take a simple voltage divider action here because the current going in is 0. So looking in here, this is as if it's an infinite resistance. So it's as if the element simply does not exist. The voltage here is simply V1 divided by R1 plus R2 multiplied by R2, our voltage divider pattern. So I get V1 times R2 divided by R1 plus R2 times R1 plus R2 divided by R1. Okay? So these two cancel out, which gives me V out 1 is simply V1 R2 divided by R1. So to get V out, I add up the two. V out is V out 1 plus out 2, which was the goal, which is my goal. And that is simply V1 R2 by R1 minus V2 R2 by R1. Okay, thankfully, what we have here is the same as here. Okay, again, there's really nothing new that I'm going to cover today. Simply apply, apply, apply 4 simple principles. So here I've used superposition and shown you a circuit. So it turns out with op amps, you should really remember that pattern. Okay? You will see it again and again and again. And each time you see it, it will save you 6 minutes of having to solve the circuit without knowing the pattern. Okay, so remember this pattern. Okay, you can pick up another 3 or 4 minutes by remembering this pattern here. This pattern is simply V2 R2 divided by R1. Okay? Imprint those 2 patterns into your brains. Okay. So those were a couple simple circuits using the op amp. We built a subtractor. And as the next step, let's go ahead and try to build an integrator. Okay? Using this little building block, we can go ahead and try to build a bunch of circuits. We can build filters, A to D converters, and so on. Let's build an integrator. Okay? So abstractly, I need to build this box. Okay? Which, when fed a VI, I want that box to integrate and give me a VO, which is VI integrated over time. That's what I want to build. So how do I go about building it? So what I'd like to do next is give you some flavor for design. Okay, how do you go about designing things with an op amp? Okay, knowing that you do not know the pattern for this yet, how do you go about designing things? Well, let's start with the following intuition. The intuition that I begin with is that if I have a current I, and remember that capacitors and inductors related to, you saw differentiation and integration happening when we dealt with capacitors and inductors. Okay? So I think we have to invoke a capacitor here, or an inductor. In this example, I'll invoke a capacitor. And notice that if I stick a capacitor in here, this current is I, capacitance C, then my voltage V naught, okay? My voltage V naught is given by what? The voltage is simply the integral of the current flowing through it. Okay, or vice versa, I is C dV dt. Okay, so if I is C dV dt, then V is simply 1 by C integral okay, so that's my so if I can pass the current through a capacitor, then the voltage across the capacitor must be a current. So notice then that V0 is related to IDT. So I have some multiplying constants and so on. But fundamentally, what I found is that if I can stick a current through a capacitor, then the voltage across the capacitor relates to the integral of the current. Okay, that's interesting. So I've got an integral in there, but I have a current. Notice my goal was to integrate a voltage. What I figured out how to do is if I can turn that voltage into a current, if I can turn that voltage into a proportional current, and then pump that current through a capacitor, I'll get the integration that I want. So how do I convert my VI to I? How do I do that? Well, let's take a stab at it. Here's my VI. Let's take a resistor R. Okay, let's take a resistor R. And remember, I need to stick the capacitor here. So I have some current I here. I don't know what the current is yet. And I stick a voltage here, and what I'm trying to do is trying to see if I stick a voltage and a resistance in series, then there is some relationship between the current and this voltage. Okay, recall I'm trying to make this current be directly proportional to the voltage VI, but turns out that I here is not equal to VI divided by R. If I was VI divided by R, somehow, okay, I'm done. Okay, if I was VI divided by R by some magic, then I've converted my voltage to a current. I feed that current through my capacitor, and VO is my integral that I'm looking for. But unfortunately, I is not equal to VI divided by R. You know that. Okay, I relates to VI minus the capacitor voltage divided by R. Okay, so I is not simply VI divided by R for all time, but I is really VI minus the capacitor voltage divided by R. And in fact, when we did RC circuits, you wrote this equation to represent the dynamics of the circuit. RC dV naught by dt plus V naught equals VI. Okay, we wrote down the circuit for a first order RC, wrote this equation for a first order RC circuit. Now, it does turn out, if we just wrap up on this wild goose chase that we went on, it does turn out that if this term here is much bigger than that term, okay? If this term is much bigger than that term, then I can ignore that term and write down RC dV naught by dt more or less equal to VI. Okay? So if that were true, this would be true, and then V naught would be more or less equal to 1 by RC integral of VI dt. Again, if this were true. If this were true for all time, then VO would be integral of VI dt. Again, remember, this is all a wild goose chase. Just write down WGC there, just so you don't get confused. Okay, I'm on this wild goose hunt here, trying to find a way to get a current from a voltage, which I can then feed into a capacitor. So this was one thing I knew, but this is not what I want. But it does turn out to be what I want when V naught is very, very small. Okay, so I see some glimmer of hope, but not quite. So it turns out that when R and C, if I make R and C very, very big, if I have a huge time constant, okay, with a huge time constant, the voltage VI, the voltage V naught looks like an integral of VI, but only when I have a very huge time constant. Okay, so I give up on that tack. Instead, I try something else. Another try. So I'd like you to notice, if you take your op amp, here's your op amp. If you take this op amp, okay, and you stick that the positive terminal to ground, under reasonable feedback, under reasonable negative feedback, what do you notice about the current? If I had a current I flowing here, okay, if I had a current I flowing here, what did you notice? Look at this picture. I had a current I flowing in here, V2 divided by R1, and because this resistance was infinite, all the current went through this the upper terminal. So this is 0 volts, and by the V plus equals V minus method, this is also more or less equal to 0. Okay, and I have a current I flowing in here, nothing goes here, so then the I must flow up there. Okay, so all I'm doing here is causing a reflection of the current from the grounded node. Okay, my current is being reflected into, or deflected if you want to, if you feel like it, into the upper edge here after coming in through this edge. So well, that is interesting. Okay, so we're just one step away from the key insight. So if I have an I coming in here, I going out there, and notice that, as I said before, this is 0 volts. Okay, so how do I get my voltage VI to look like a current, to become proportional to a current? It's simple now. All I do is put a voltage VI and put a resistor R out there. Okay, if I do that, then since this is 0, the current I is given by VI divided by R. Okay, I've got where I want to be. So by using an op amp and using the fact that the minus node here, V minus, is at the same potential as V plus when there's negative feedback, then I can stick a resistor here, and because this is 0, the current here is simply VI divided by R. Okay? I've gotten to the first place. Now all I need to do is simply pump this current through a capacitor, and I get the integral of the voltage becomes the integral of the current. That's easy. I stick my capacitor here, and I get my answer out there as VO. Okay? Notice that when I do this, let's say this is plus minus VC. Okay, so but this is 0. So V naught is minus VC. Again, I'll keep emphasizing it maybe 17 times throughout this course, that if this is 0, then the output here is related to the negative of this voltage. Common mistake. Okay, I will be very upset after doing all this if I see this mistake happen, in any of the future homeworks or finals or whatever. Okay, this should not happen. This is so V naught is a minus, the minus sign here, VC. Okay, and I know that if I have a current I through a capacitor, what is VC? If I have current I through a capacitor, then this is simply T I dt. Okay, and I, by design, is so I have my integrator. Okay, it's a two-step process. I stuck a resistor here, so the current became equal to VI divided by R. Then I took that current and pumped it through a capacitor through this terminal here, and the voltage across the capacitor for a current I is given by this expression. Okay, this is capacitors 101. Okay, capacitors 101 says that the voltage across the capacitor is simply 1 by C integral I dt. Okay, another way of looking at it is the voltage across a capacitor is the current through a capacitor is C dV dt. Okay, this is simply the integral form of that equation, and I'm done with my integrator. Okay, so this is another very common building block. Okay, remember this. Okay, most of the circuits we will be seeing with op amps simply involve something here and something here. Okay, and the output in this inverting connection is the output times, if it's a resistance, it's simply R2 divided by R1. When it's a capacitor, I get the integral form looking like this. Yes? So can someone tell me where the negative sign went? The blackboard ate it up. Good catch. Okay. Okay. After all that lecture about watching the negative sign, so after this little bit of a faux pas here, now I will be doubly mad if you guys make that mistake. All right. Okay, so let's. So now that we built the integrator, I could give this out as a homework problem, and you should be able to design a differentiator based on what you've learned here. Okay, we now have the tools to go and do some design like this, but we don't have any more homeworks left, so I guess I'll go ahead and solve this for you right here and do the design for you. So the building block that we need looks like this. D by dt here So let me take a VI and stick a VI in there. That's what I want to build. Okay, what I built here is that different integrator box. And what I'd like to do now is build a differentiator box. So how do I go about doing it? Okay, I'll go really slow here so you will have some time to think about it for yourselves and see if you folks are, are crack op-amp circuit designers already, if you have the right instincts here. Okay? So again, when you see differentiation, integration, think capacitors or inductors, doesn't matter. Or in fact, as a homework exercise, you may want to go back and see how you can get a similar effect using inductors. Okay, can you play with inductors and get a similar effect? Okay. So inductors are devices that are a dual of the capacitor. So whatever we do with capacitors, there must be a corresponding way with inductors. Okay, so you can try it out in your spare time. Okay, let's go back to this one here. So I'll stick with the capacitor way of looking at things. And I need a differentiation now. So remember this. So if I have a VI, okay, and I stick this across a capacitor, I have a current C and some voltage VC across the capacitor. Okay, what does I relate to? I is simply C dV dt, dVC dt, and VC in this case is simply C dVi dt. So if I can stick a voltage across a capacitor, like if my input voltage is stuck across a capacitor, then the resulting current relates to dVi by dt. So here we have the opposite problem. By doing this simple trick, I can obtain a current that has the right form. Okay, now what I need to do is somehow convert that current into a voltage. Okay, because the abstraction that I need is a voltage to voltage. So the next step, what I need to do is somehow convert a current to a voltage. Okay, so how do I go about doing that? So again, remember, for the op-amp, if I have a current I flowing here, then by the reflection property, I gets pushed up into this edge, provided that the whole circuit is working with decent negative feedback. So given this trick, what I can do is say, look, suppose I did this. So remember, my goal here is how do I convert a current to a voltage? Okay? So I have a current I coming in here, and I can turn that into a voltage because I know the current must come out here. I know this current must come out here. So all I have to do is stick a resistor in there. If I stick a resistor in there, what is VO equal to? So VO is simply IR, right? Yeah, that's right. Okay? So VO is, I get I here, so the I pumps through here. Remember, what comes in here must get reflected up because the current going in here is 0. Okay? So all the I must come out here. So that I must pump through this resistor. So the drop across this resistor is IR. That's the voltage drop across that resistor. And since this is the ground, this is at a virtual ground, the output here is simply 0 minus this drop, which is minus IR. Okay, so I've gotten to where I want to be. I have my my current I have it being converted to a voltage. Okay, So I've taken my current, and I've been able to convert that into a voltage by sticking a resistor in here. Okay? So as a final step, I simply need to produce the current. Okay, and that's pretty easy to do. Abstractly, what I need to do, again, this is design here. Okay, so we'll talk about abstract stuff. So, like if I have a voltage VI, I need to produce a current which relates to C dVi dt. And I know I can do that by simply doing this. Okay, by doing this, I know my I is C dVi, correct? So if I can get this effect, we put this in quotes because that's my pattern. I'm looking for a pattern where a voltage VI is directly applied across a capacitor, and when that happens, the current relates to C dV dt. Okay, so let's go back to our op-amp pattern here, op-amp circuit. So far I have achieved okay, I just repeated this out there. And so somehow I need to take this pattern here and learn from that pattern and apply the pattern here. Okay, so what I can do is, this is a ground node, correct? Now the poor little capacitor, what does it care whether it's a ground node or a virtual ground node? Okay, as long as it's a 0-volt node down here, what does it care? Okay, so what I'm going to do is stick this point, not here, but into a virtual ground node. Okay, I'm going to grab that point, take it here, and stick it here. Okay? So the poor little capacitor doesn't know the difference. I have really suckered the little beast. So this is VI. Okay? Remember this. This is my I through the capacitor is proportional to C dV dt. Instead, what I've done is taken this guy and stuck it here to get something like this. Okay, just remember these 4 or 5 little tricks, and you apply them in op-amp circuits again and again and again and again. So this is VI. This is my virtual ground. So as far as this poor little capacitor is concerned, it's chugging along merrily, thinking that it's connected to ground. Okay, little does it know it's only a virtual ground. All right, but the current I here is simply C dVi dt. Okay, and since that current is C dVi dt, that current flows through here and gives me V naught as IR. So V naught is simply minus R. Let me substitute for I there, is C dVi dt. Okay, so notice then that my V naught is now proportional to dVi dt. Okay, so V naught is some RC time constant, okay, times dVi dt, and therefore I have my differentiator circuit. Okay, so remember this as a closing thought. Remember this V plus more or less equal to V minus trick, and to the extent possible, simply use that trick to analyze op-amp circuits under feedback and not in saturation. Okay, just remember these two. So very quickly for the demo, I have a square wave input. I have a square wave input here to the op-amp. That's my VI to the integrator, and this is the output V naught. So integral of a square wave is a triangular wave, as you can see. And we'll do the same thing for a differentiator. And for the differentiator, I input the square wave to this differentiator circuit, and I get this, whenever there's a sharp rise, I get this huge negative spike and a positive spike because of the minus sign. So this is the differentiator circuit when I feed this into the op-amp. Okay, thank you.